Rocks move themselves across the desert. The image grabs you because it feels like a magic trick left running overnight. We're going to test it. We'll track what actually nudges those stones, why the motion looks mysterious, and how ordinary physics hides under a dramatic outcome. By self-moving rocks, people usually mean the sailing stones on flat, dry lake beds called playas. The most famous site sits on Racetrack Playa in Death Valley, California. The legend stuck because the trails look surgical. Long parallel lines snake behind heavy rocks, sometimes crisscrossing with crisp right angles, as if someone steered them in secret. Mystery sells, so rumors spread. Tourists whispered about pranksters, magnets, or rare hurricane winds, while books labeled the tracks unsolved to keep the page turning. Here's the core mechanism in plain words. Thin ice, a shallow sheet of water, and a light wind combine to reduce friction and give rocks a gentle push. A playa is a broad, hard pan of fine clay that floods occasionally. After rare winter rains, a film of water spreads across the surface and freezes overnight into a clear, brittle sheet. Come late morning, sun and breeze break the ice into floating plates like window glass. Those plates bump against the stones and behave like slow, wide sleds that push the rocks over slick mud. Because the water film cuts contact and the ice shares the load, the needed wind is small. We're talking modest breezes, not desert gales. The rocks move slowly, often too slowly to notice unless you watch for hours. They slip forward a few meters in minutes, then stop when the wind falls or the ice jams. Field observations clinched this in the early 2010s. Researchers placed GPS loggers on select stones, set up time-lapse cameras, and watched during a wet, cold season. They recorded multiple moves in daylight, with thin ice plates pushing the rocks across a few centimeters of water. Trails formed in soft mud and hardened later under sun and wind. Earlier decades had hinted at ice. Park staff and scientists saw freeze-thaw patterns, thin water, and seasonal timing that favored winter mornings after storms. But the direct evidence was the turning point. It replaced guesswork with logs, photos, and matching weather notes tied to specific days. Counterexamples test the rule. Some trails show sharp turns or sudden starts, which people took as proof of steering or strong jolts. Ice plates answer that cleanly. When plates pivot or pile up, the push direction changes. When a rock meets a ridge of cracked ice, it pauses until another plate drifts in and resumes the shove. Another counter-idea says hurricane-force wind alone could slide stones over dry clay. Dry clay grips too much, and tracks appear during seasons when ice forms, not during hot windstorms. Prank theories also fade under scrutiny. Many trails stretch hundreds of meters across open ground, sometimes with dozens of stones moving in parallel on the same day. Easy to match with weather, hard to fake without footprints. The timing matters because it explains the vanishing act. Stones often move on a handful of still mornings each winter, when no crowds stand watching, and the playa is closed or quiet. By noon, the water evaporates, the ice melts, and the mud starts to firm. Visitors arrive to a dry floor carved with fresh, precise trails and no visible cause. This is a case where correlation and causation part ways. Long trails correlate with windy seasons, but the cause is not brute wind alone. It's wind plus water plus millimeter-thin ice that lowers friction and organizes the push. Other players show similar behavior. Anywhere you have a smooth clay pan that floods shallowly in cool weather, you can get slow stone motion under gentle wind. Variables shift year to year. You need enough rain to wet the surface evenly, cold nights to glaze it with ice, a clean pan without ruts, and light winds to drift the plates instead of shattering them into slush. Some winters bring all four for a few mornings, some bring none. That's why the phenomenon looks sporadic, then suddenly prolific. Rock shape and size matter, but less than you'd expect. Flat-bottomed stones catch the plate's shove well. Taller stones can plow or tip, yet even multi-kilogram rocks move when the ice plate is broad and the mud slick. The playa's surface texture also sets the stage. Fresh clay crust, unbroken by footprints or vehicle tracks, allows long clean lines. Scars or ripples break plates and divert the push. Researchers found no need for exotic forces, no magnet fields, no weird electrical effects, no vortices swarming out of nowhere. Ice plates provide a distributed hand. They grab many points along a rock's edge, share force, and make motion straight and smooth compared with water alone. If you want a mental model, picture a puck under a thin, melting glaze with a gentle fan blowing. The fan does not need to be fierce because the glaze shrinks friction, and the puck rides on a moving sheet. The slow speed explains the eerie look. Our eyes expect fast forces to leave bold marks, yet here a delicate, prolonged nudge writes long trails with surgical precision. What remains uncertain? The exact thresholds vary with each season and site. How thick the ice must be to avoid shattering, how deep the water can get before waves disrupt tracks, and how clay chemistry affects slipperiness. Those uncertainties tweak predictions, they don't rewrite the mechanism. We can say thin ice and shallow water with light wind, and be right most winters that produce new tracks. A fair alternative view says some rocks might move without ice under very slick, fully saturated mud and steady breeze. That can happen briefly, but the cleanest, straightest, most coordinated movements match the ice plate mornings. As of recent studies, the best records show clustered moves during sunny, cold mornings with a few millimeters of water and a few millimeters of clear ice. Under modest winds you could comfortably stand in. It's worth noting the conservation angle. Footprints and tire marks ruin the surface, trap water into rivulets, and break future ice sheets, which means the phenomenon relies on leaving the playa undisturbed. So how do you carry this beyond one desert? Use the same logic on any dramatic trace left by ordinary forces acting slowly. Ask 3 questions. What lowers friction here? What supplies a small sustained push? And what preserves the evidence after the push ends? If you can answer those, mysteries shrink. The story becomes a patient cause with a photogenic effect. Here's the rule of thumb. When you see a spectacular outcome with no obvious energy source, look for slow causes that operate only under narrow conditions, especially ones that switch on when people aren't watching and switch off before they return. Tiny inputs over long windows can beat big pushes in bursts. Ice plates drift, rocks glide, trails harden, myths grow. In short, the self-moving rocks are not self-propelled or supernaturally steered. Thin ice, shallow water, and light wind do the quiet work when the playa is glazed and slick. The distilled takeaway is simple. Dramatic lines can come from delicate forces given time and the right surface. Subscribe for more myth versus reality and tell us which beautiful mystery you want unpacked next.